So, yep, welcome back. And now that you have seen some of our own, uh, which one is this? Oh yeah, okay, sorry. Okay, yeah, this is the one, the right. Now, maybe we can do a quick poll right now, since we have a lot of people who've been working on snow leopards for many years and some people who've never worked on snow leopards out in the field. Let's do a quick poll here with a simple yes, no answer about how many of our participants have actually seen a wild snow leopard in their life. Just press yes or no. How many of you have seen a snow leopard in the life, a wild snow leopard in your life?
A wild snow leopard in the wild while you're in the wild.
While you're in the wild. Okay, we have 76% votes are here. Anybody else? That's it? Okay. Wow, that's an incredible number. 70% of our participants say they've never seen a snow leopard in the wild. All right. Now, I'm going to throw a little challenge here. I'm just zooming in a little bit on this picture, on the previous picture. Can you see snow leopards? In fact, can you count how many snow leopards are there in this picture? And we'll have a new poll now. There we go. How many snow leopards can our participants see in this picture? We can give them some time, Justine, maybe. Okay, oh, Ranjana is.
I feel like cheating.
No.
Raki, no cheating.
Okay, I'm not doing anything.
Raki, you should be a co-host and you shouldn't get to cheat anyway. Okay, come on. We have 15 more seconds.
I don't know how you're cheating, Raki, because I'm not. I still can't see. So we have 3 responses so far. So the rest of you, we're going to give you.
Can't see the poll. I lost it.
If you don't see any, just press 0, please. We have 6 out of 14.
There's no 0.
Oh, there's no 0.
I took away the 0.
You took away the 0. Ah, well, okay. Maybe someone would say there is none.
Some estimates are coming in on the chat because maybe there are issues with the polling, but that's totally fine if you guys in the chat. Okay, I'm going to end the polling now. Is that okay, Koustubh? We have around half.
Yeah.
Any last estimates?
2, 2, 2, 2. Okay. All right. One says 3. Wow. Okay. All right. I think we can end the polling, Justine. Okay. So, 25% say there is 1 snow leopard. 63% say there are 2 snow leopards. 1%, I don't know who this is claiming that there are 3 snow leopards. All right, let's go to the next slide. Now, let's do the poll one more time, please. And this time, please tell us how many do you see? Come on, this time we should get the answer clearly. Poll again, please. Thank you, Justine. How many snow leopards in the picture? 2. Okay. Okay, we have 35 seconds. 2. So Hamera, Helena, are you able to, Bikram, are you able to see the poll? Can you see the poll and are you able to enter your vote? Okay, great. Right. Okay. Now I'm just curious, since you put it on the chat, I wasn't very sure if you could get it.
Sometimes it disappears,
yeah.
and then it comes back.
Yeah.
We have around half the votes in.
Okay. Come on. 7 more people you must vote in. There's no wrong answer, so don't worry. You remember in statistics, there is a probability for even, 0 to be true or 5 to be true. So don't worry. Bikram sees 3. Okay. All right, we'll close it in 2-3 seconds, Justine. Yeah, let's close it now. Okay, we have 4 people who've not voted. All right, so again, we still have 80% people who claim that there are 2 snow leopards, and there are 2 people, 20%, who claim that there are 3 snow leopards. Pooji has come back in. Okay, now let me show you the results. Now, what's fascinating here is that only 20% of the total number of observers have been able to count the right number of snow leopards in this image. If you look at the tip of the tail of the snow leopard, you will notice the third snow leopard who's hiding. That's actually the mother, and these 2 are the cubs. Now, this is one of the most incredible pictures of 3 snow leopards in a frame, and you still miss out most of the times. But this is exactly where the effect of that red devil which we discussed about last time comes into action. Now, clearly, the snow leopard is a difficult species to see, but not that difficult to photograph on camera traps. This is one of my favorite pictures of a snow leopard from on camera trap from a part of Ladakh by a friend, Bezad Larry. And yeah, I mean, most of you who know where to look for a snow leopard through the scrapes and other signs, on saddles, in canyons, under overhanging rocks, it's not that difficult to photograph a snow leopard on a camera trap. Now, before we move forward, we'll talk more about camera traps, and we'll be talking more about setting camera traps in the 3rd seminar. For now, I'd like to show you the life of one of the 35 snow leopards we've been following in Mongolia using telemetry. In fact, there is a longer and a more complete version of this you can find on YouTube. Justine will be able to share that separately. I've just created a smaller version for us. So in April 2011, our team collared the 5th snow leopard as part of the long-term ecological study. Now, her name is Anu, and if you look carefully, Anu seems to be moving about in this sort of a circular or an oval region, and her movements are pretty concise until at least the spring gets over. Now comes summer and her movements kind of change a little bit. She's still living around that little spot in the center of this activity range, but there's a different boundary, as you can see, bound by it. And then of course she goes out for forays once in a while. Now in the winter, same snow leopard, but she's using an entirely different pattern of movement. What you see here is she's beginning to explore new terrain. Perhaps she's looking for denning sites or looking for a partner or whatever. But one snow leopard, similar activity center, almost the same activity center, but over different periods or over different months, this one snow leopard seems to be using different parts of her activity range. In other words, while their ranges are well defined over a short period of time, over a long period of time, there is a chance that sometimes even the activity center might change. They might move into a new area, or some other snow leopard might push them away, or in the longer period of time, snow leopards are also likely to die or be joined by a new recruitment of snow leopards. So these are some of the very basic parameters or basic understanding of most species that we know, that they all tend to have clearly defined activity ranges which change. So an animal annual home range of a snow leopard might be much bigger than its seasonal or a much shorter, even monthly activity range. Now, here you can see many snow leopards with their respective home ranges, which are defined as these. You can see. Let me hold on. I need to make that optimize share. Video. Okay. Now, just one more second, please. Right. Yeah. So as you can see, these different individuals have different activity ranges, and they can be defined by these kernels. And typically, the outermost kernel, we call it as the 95% kernel. But one thing we need to keep in mind right at this point is that all single season population estimates assume that the population is closed to changes during the sampling period. And this is more or less what one of the groups had also discussed, that we do not want the population to be changing a lot during the sampling period. They may change over a longer period of time, but that's something we will deal with separately we can deal with separately using open population models and so on. But we also have to remember that there'll never be a truly concise period when a population will be closed. There is a probability of an animal dying or a new animal coming into a population at any point in time, whether it's 10 days, 20 days, 30 days, 90 days, or 4 months or whatever. What we need to do is we need to find a concise period when this can be considered to be, the population can be considered to be closed. And a few violations do not kill your analysis, so don't worry too much. All you do is you relax your assumptions a little bit, but your analysis could still be fine. Now, let's start. Let's assume that we know this one snow leopard whose activity center, or let's say the center of its universe, is this coordinate 0 and 0. Now, this one snow leopard can be, let's say it's our first virtual snow leopard. For simplicity's sake, we'll remove the snow leopard icon and we'll denote it with a little dot here. Now, this is how a virtual snow leopard would move, and these movements we have simulated using very similar patterns as those of a real snow leopard. What you notice are a few things that might be going on here. The animal seems to have an activity center. It moves about but keeps coming back, right? If you look carefully, the animal is, going about but keeps coming back. It's almost, it seems to have some sort of a range that it typically does not go outside, at least in this period of time. It's staying within that range, and it keeps coming back to the center of it. So if you look carefully, you will also notice that different parts of its activity range are being used to different extents. Central parts are used more. You will see more density of dots there. As you go further away from the center, you see fewer and fewer dots. So in other words, look at it this way: for any creature, be it a snow leopard or a tiger or a leopard or whoever, its movement patterns can be defined through a few parameters. The first one we call as the activity center. Now, activity center is like, you can think of it like your home, right? Now, you may go to your workplace, spend 7-8 hours, but you always come back. You might go to a party, but you will come back. You might go to meet a friend, but you will come back. Now, in other words, your home is the activity center, which is where you belong. And any other places where you visit for different durations, you might go to the office, you might spend 8 hours there. So you visit the office, let's say to a certain extent. Now you might visit a friend of yours few times a week, but you don't spend as much time with that friend as much as you spend in the office or at home. So you are spending a relatively lower period of time to that friend's place. And then you might have one of those relatives who you don't like much, but you have to meet out of obligation. So you might end up once or twice visiting that person in an entire month or 2 or 3 months or whatever. So let's think of the activity center or the activity range as yourself and how you use space, your own space. The only difference here is animals use space almost in a way as a function of distance, and the distance is not always straight line. It can be ecological distance. We'll talk about that separately, but it could be the least cost path from point A to point B, or it could be the straight line path from point A to point B. But typically, this is how animals seem to use the spaces. Now let's move the animals' movement around this activity center again. This time I'm doing it a little faster to save time. What you will also see on the right-hand side is I'm plotting the distance from the activity center in 2 dimensions. You will notice that in due course of time, the histogram starts to look like a normal curve. Now you remember when we did our exercise with Lego, when we split it into a group of men and women, we started seeing a normal distribution. Here again, if you look carefully, over a period of time, the number of locations of the animal close to its activity center are much higher than as you go further away. Same example that I was talking about. You live at home. Think about like we are living in a city where there are no mobile phones, right? Now, if someone has to find access to you, the best way for that person would be at a random point of time in the day. That person doesn't know what time your office timings are. For a person to get the best chance of getting hold of you is to call you at home. And if that person calls 10 times at home, there is a chance that at least 5 times he will find you. Now, if that person wants to contact you and he doesn't have your home phone number, but he has your office phone number, if he calls you 10 times, there might be 3 or 4 times he might get you if he's calling a random number of times. Similarly, that person also knows your not so very fond or not so very favorite relative. The chances of that person getting hold of you through a landline phone call are very less, but there's still a chance that further away this person will be able to get hold of you. So think about what we start with is the activity center being our home, and as you move further away from the activity center, the chances of you being detected away from your home at different distances, in this case the distance is we're talking about different places, it reduces. And that's precisely what's also true with species. Look at this very closely. Same images, I'm just presenting them in slightly different formats again. Now, if you look at this closely, you will notice that a contour, I've just created a contour of 95% of the locations. Now, you all remember we were discussing these lines last time. These were the lines we were discussing as the 95% confidence interval. All I have done is I have drawn the same line on these coordinates here. And what we see is some sort of a range contour building up. What it basically shows us is that if we have a lot of coordinates, we can use it to define an animal's range during a period of time. And in other words, let me show you something here. Now, in the last session, you might recollect, we spoke about means, we spoke about variances, we spoke about standard deviation and 95% confidence intervals. Now, let's say this is how our the mean looks like, right? We all remember this curve. You have a mean and the distribution is normal. So there will be fewer and fewer and fewer frequencies as you move away from the center. Now, let me plot again. Yep, so the mean we denote it with mu. Forget about what mu stands for. Just remember the mean here. Now, you all remember the standard deviation. Standard deviation is an estimate of variance, is a metric of how much error is there in my data. And some of you might remember sigma is a term that we typically use for standard deviation. In other words, if I use sigma square, that stands for variance. So if I know sigma or sigma square, either, I mean, these are interchangeable, but sigma is the other parameter that we are aware of. And we might know sigma for this particular value. It would stand somewhere over here, right? In fact, if we know sigma, then you all might remember we discussed about 95% confidence intervals. And if you recollect, there was a term we were using, 1.96 times standard error is what, and then this was plus and this was minus. Now, instead of 1.96, I've just taken the luxury of simply just calling it twice sigma. So roughly speaking, if we know 2 sigma, that's somewhere between 95-96% of the confidence limit. So somewhere around this is where my 2 sigma would stand, and that denotes the range in which the data is distributed. So if you have to relate back to the activity range, now can you think about it in the same way? So all we are really talking about here is a 95% confidence or the 95% activity range is simply twice the sigma, approximately. I'm not saying exactly, but roughly twice the sigma. And what is sigma? If I have a curve like this, I can estimate sigma, assuming this is a normal distribution. I will get a sigma value, and twice of that would be this 95% confidence limit, or in this case, the activity range. Now, same thing, I'm just plotting it one more time. This time I'm plotting, instead of plotting okay, let me just show back. Here what we are using is, if you look closely, here we are using the y coordinates 0 to whatever, x coordinates 0 to maybe 1000 and 2000 and so on. Now, instead of the x and y coordinates, I'm simply estimating the distance from this point x, which is the activity center, to each of these points. And when you see them plotting up, nothing is changing. The same animal is moving. If you look carefully, the animal is moving around this space. And what you see here is the activity center is slowly building up. And as the distance from the center increases, you have fewer and fewer encounters of the species, right? Now, this is a fairly reasonable, why did it stop? Oh, yeah, it's a fairly reasonable depiction of how an animal's distribution would look like. Now, when look at it closely, do you see there is an interesting pattern here? In other words, if I just plot it like this, do you see, if I could have extended it like this, I'm actually looking, this would have been a normal curve. What I'm doing now is I'm looking at something which is half of that normal curve. And that's what we are looking at right now. We are looking at the half normal distribution curve of the same data, instead of both sides and 0 to x in the positive direction and 0 and x moving in the negative direction. I've just simply estimated the distance from this activity center. As you go away, you have fewer and fewer encounters. Does it make sense till now? If you have any questions, I have a chat window open. Oh, well, yeah. Okay. Give me a second. Okay. So I'm going to quickly move from here to a realistic scenario. Oh, I need to clear my drawing. Now, what if we have some cameras in this one snow leopard? Now, this is a very typical situation where we have only one snow leopard using the space. We have, let's say, 5 camera traps. Now, what if we set up these camera traps somewhere? We have no idea where the snow leopard's home range is, right? We have no idea where the activity center is. We just have these 5 cameras and we know an area roughly where the snow leopards are. So if I set up these 5 camera traps there, what would it look like? Over time, my cameras would detect animals. The camera traps would detect animals every few days or every few weeks. And these blue dots, if you notice here, these are the actual captures of snow leopards while they are moving about the space. Now, on the right-hand side, you can see it's the same curve, nothing new happening out here. But on the left-hand side, you see that whenever a snow leopard is crossing by or passing through the camera trap, it's getting trapped. Now, if I set up my cameras for a long enough period of time, I might end up with substantial number of captures. In this simulation, we have 16 captures over 500 locations, right? So 500 locations, maybe, if we are collecting a location every hour, we are saying, or every 5 hours or every day, let's say over a 500 days, we have 16 captures of this one snow leopard. Now, what it means, in other words, is this one, so we get a snow leopard here, then we get two captures on this camera, then we get 1 capture on the camera which is slightly further, then we again get a capture on the first camera, then we again get a new capture on the second camera, then I get a capture on this camera, and so on. So what you see here is, as the time passes, I am getting a different number of captures on different cameras placed at different distances from the activity center. Now, why is this important? Is because you see the number of captures as a function of distance from the activity center is sort of taking a shape. Now, it's taking a shape which is very similar in a way to the shape of the okay, hold on. Yeah, it's very similar to the shape of the histogram that's building up behind, which is the movement of the snow leopard about its activity center, right? Is that clear till now? If you have questions, please feel free to. Okay. Right. Okay, let me put it more simply out here. Now, what you're seeing here is the captures on these cameras here are more like a subsample of the animal's distance from its activity center. You see a very similar pattern taking shape in both cases, right? In reality, what we don't always have is so many cameras within a single snow leopard's range. We might have 2 or 3, but we usually try to maximize that number. And this is still a very good case where you have enough encounters, but you will always have partial information. We will never be able to have like 500 encounters over a period of time of one snow leopard, right? You might end up with, in this case, there were 16 encounters over a 500 days period, right? So in this case, what you're ending up is sort of a partial information. You might have some bumps here, you might have a little trench here, and so on. But generally speaking, our data is taking a shape which is very similar to the one of the shape behind. In other words, you do see a pattern which is similar to what the half normal distribution in this particular case, what the half normal distribution of animals as a function of distance from their activity center is. So even though it's partial information, it's still very valuable as it follows a certain predicted pattern. Now, the problem is, what we are really expecting here is to know the activity center, right? We believe we know this is the activity center, but in real life, do we ever know the activity center of a snow leopard unless you have them collared and followed on using telemetry? Perhaps not. All you know is that the activity center could be somewhere in this large space, but we don't know what the activity center is. It could be, it could be somewhere at minus 500, plus 500. It could be at 1000 coordinate, or somewhere. We don't know. We probably would never know unless we do telemetry where the actual activity center of a snow leopard is, right? Now, we also don't know what the range is. Now, we claiming to know sigma, but in reality, when you collect the data, you don't really know the sigma. If you don't know the activity center, you don't know what the sigma is. It could be 300, it could be 100, it could be 500. It is an unknown. Now, sigma in this case is a parameter which denotes what the range is. In one case, the range could be twice 500, which is 1000. In another case, it could be twice of 100, which is 200. We don't know. We have no idea about what sigma in real life is, right? And that's something we will get to know. We hope to get to know through some of our data empirically. Okay. Lastly, we don't even know what the number of actual encounters. Now, in this case, if you remember, we were lucky that we had one camera trap which was right next to its activity center, and it ended up with, let's say, 8 or 9 encounters. In real life, when you set out the camera traps, you have no clue where the activity center is. So you will not know, even if you know the density, you will not have a priori knowledge about how many encounters should I get at the activity center. Like in this, or in other words, if you set up a camera for 40 days, 45 days, as Barkat was suggesting, you might end up with 20 encounters at the activity center. For instance, hypothetical scenario, we managed to get the one camera somehow at the activity center of a snow leopard. In 45 days, I get 20 encounters. In 90 days, I end up with 35 encounters. If I leave the cameras just for 20 days, I might end up with 4 encounters or 5 encounters. In a particular session that I'm analyzing, I will never know in advance what number of times will I encounter a snow leopard if my camera by chance is set up at the activity center. So there are, literally speaking, there are 3 unknowns. Now, had it been one unknown and maybe 1, 2, or 3 or more knowns, we could have used simple algebra to come up with that unknown. In this case, we have one equation with 3 unknowns and literally a few data sets. In our case, the data is the number of encounters of in our case, we have our data is these encounters. This is the data that we have. That's all that we have. We don't know anything else. Now, how do we use this data to come up with 3 unknowns? In our case, the unknowns are sigma, D. I'll tell you what D is for now. Consider it activity center. And the third one is lambda 0. How do we find these 3 unknowns just based on this data? Now, this is where there's a very powerful tool which has been helping statisticians. To be honest, it started with with people trying to predict at gambling, and that's the origin of statistics theory as well. But a method called maximum likelihood is this is where it comes in very handy. Now, maximum likelihood, what we will do is, so don't worry too much at this point in time. In the last session, we will do an exercise where we will do an exercise on maximum likelihood with some example. But for now, let's consider it like this, that you have a single variable. Now, or let's say in this case, you have two variables. Okay, let me show you these two variables. So let's say this is sigma, and let's say this is encounter rate at activity center. For example, I know none of them. So what I do is I take my data and I put it here and I say that, okay, for my data, will the value of lambda being -4 and that of sigma being -4, will that result in a data where I have whatever number of my encounters were, right? So in other words, I provide data to the solver, and I ask it every time, what is the likelihood of my data being true for this value of lambda 0 and this value of sigma? Now, what the solver does is it goes to each point in this space. And when it goes through each of these points, at some point it starts seeing, aha, I'm reaching, I'm reaching a peak. And those of you who may have some mathematics background will remember integration is one of the ways how you can estimate the maxima and minima of a variable. But ultimately, it reaches a point where it realizes that, okay, there is no point above this and there's no point below this, which means I have reached the maxima. In other words, this is the point where the solver has tested that given this data, the solver has tested the likelihood of all possible values of lambda 0 and sigma to be for the model to be true. And when you reach a peak, you stop and you report this value, whatever was the value of lambda 0 in this case, let's say it was -3, and sigma in this case, let's say it was +2. So these become the value of lambda 0 and sigma. So this is, in simple words, what SCR does. It uses a similar approach and runs on a hill of all possible values of lambda 0, sigma, and also density, because we have three unknowns. So now you have to think in 4-dimensional space. And it ends up looking for the best possible location where, if I have this data, what would be the best value for a lambda 0 density, D for now, D and sigma to be what they are. Okay, does that make sense? Because now what we will be doing is we'll be changing gears. Okay, there's another very interesting example I've written here. So think of, in other words, you're basically walking about with a torch with very short light. So at every point you look around and you say, okay, oh, that point is higher than where I am. So I just take that step there. Now from that point, you look around, you say, okay, where I came from, that was lower than me, but to the right side, there's a higher point. So you move to that point. And ultimately you keep moving short distances. And at one point you end up at a position where you're at the highest place, where there's no other neighboring place which is higher than you, and you stop. And those are the values, we use those values of the unknown parameters, whether it's for density, sigma, and encounter rate, and use them as the most likely values of these three unknowns. Okay, moving on. So we did what we did for one snow leopard. I hope it's clear. With one snow leopard, we can do the same thing for two snow leopards. Similar patterns, similar movements. Instead of one, now we have two individuals. We're calling them snow leopard A and snow leopard B. Just like before, here too, we will get multiple encounters of two snow leopards on different cameras if we set them here, right? Sorry, there was a Okay, I'll come back to your question, Barkat, a little later, and maybe after this session is done. Not this session, but after this presentation. Right. So just like before, here too, multiple encounters is what we can expect. Now, what if we have not just one or two, but in this case, I have created a virtual population of 26 snow leopards for our study area. Now, these X's show their home range centers, activity centers. We need to think of home range as slightly different here. If you're thinking in terms of home range, camera trapping does not happen for full year, shouldn't be done for full year. Why? Obviously the population opens up and there are, the activity ranges change. But for a short period of time, we would rather calling it a home range, we try to call it activity range. Now, these 26 snow leopards, and I've made 26 because I could easily name them A to Z. I didn't want to add A1, A2, A3, and so on. So for now, for simplicity's sake, we have 26 snow leopards in this study area, which has a coordinate system, our own coordinate system between 0 and 5,000 and 0 and 8,000. Now, these X's are showing the activity centers of each of these 26 known snow leopards in this population. Typically, as Justine mentioned at the beginning, we do it the fun way using M&Ms that we try to not eat during the exercise, but obviously once the exercise is over, we all get our own M&Ms to eat. So sadly, because we are having to do this online, and since you all are not around, I don't want to end up eating too many chocolates. So we decided to not use M&Ms, but please treat yourselves after this class and have some M&Ms or gummy bears or whatever is of your interest once the workshop is over. What we will do is instead of M&Ms, we have a virtual snow leopard population animated in this space. Now, this population of 26 snow leopards are using the space as per their individual activity around the activity center and along an activity range, which we can define as sigma. You remember sigma, 2 sigma. So roughly we can define the activity, the space use around the centers using the same principles. Each of these snow leopards don't have exactly the same activity range. I have kind of randomized it a little bit to make it as close to reality as possible. What we have also done here is we've also kept them homogeneous right now, but in reality, you might end up with females with smaller activity ranges, males with larger activity ranges. We can deal with them specifically. For now, we are assuming that this is a population which has a homogeneous activity range. It does not change much. And in this case, what we have is 50 camera traps. That's what we started with the exercise today. So what we need to do is find good locations to set up those 50 camera traps. So they end up doing the capture exercise for us. What we do need to leave these camera traps out in the field is for several days so that each snow leopard gets enough opportunity to get its selfies taken. Typically, camera trap designs are either uniform. A lot of people prefer uniform because it's easier to design. We discussed it the other day. But sometimes to have a uniform design is not practically possible. So you end up as close to uniform as possible. There are some new works which have come out which recommend cluster design. Now, those design issues, we'll talk about them later. For now, just assume that there is this setup of camera traps which has been set out in a certain area within the study, within our area of interest to estimate the snow leopard populations. Remember, the snow leopard population, those X's, they are randomly distributed in space. They're not distributed as a function of a particular covariate, at least in this space, right? We will do that as an exercise in the fourth session. But for now, we are assuming the population to be randomly distributed in space. In other words, the Spiti map that you discussed, we saw today, that had randomly distributed snow leopards. So this is more like a Spiti kind of a design. Now, in real life, what we do is we generate 3 types of data sets when we are conducting camera trapping. The first one is where cameras are. Now, this is perhaps the simplest of all the data sets. So when you're setting out your cameras, you know where you've set up your cameras, and that's about it. So all you need to know is where the camera locations are. Here, you see, I knew where each of the camera traps are. So I've named them C1 to C50, and we've named them as C1 to C50, and each camera has a specific location. Now, this is the data you collect when you are setting up the camera traps, right? I believe this would be one of the easiest data sets to get. Many times, having said that, many times we've had problems where people have set up the camera traps and forgotten to take the precise location, and that can be a fatal error. Please try to have your locations taken as precisely as possible where the camera traps are set, because ultimately we have to estimate some values which will be a function of where that location is. Now, so that was data type 1, which is we can call as a trap location data or trap data. The second data set is the capture data. Now, this is while the first one is collected when you're setting up the camera traps, this is the data that you generate when you have collected the camera traps. Now, this is, I mean, there's a huge process from getting the cameras to identifying individuals, and we will have the next entire seminar is going to talk about that. But the bottom line being that there are 2 important things here to remember. Once you have identified individuals, please, only those individuals should be listed as identified with about who we are almost 100% certain of their IDs. If we misidentify, we might end up providing SECR the wrong data about that encounter histogram, and it may either grossly underestimate our population, or it might, on the other hand, overestimate the abundance in 2 different scenarios. So individual ID, for whatever it is worth, it's actually one of the most important things to take care of. And any image, any photograph which you are even slightly not sure of, feel free to junk it out. The spatial capture recapture analysis is pretty powerful, and it can deal with a small percentage of discarding of data. So don't worry about that. But it's very, very important that individual IDs are taken correctly. Now, what you're seeing here is from these are the number of encounters on different cameras. Now, C1 has 8 encounters. Now, there could be multiple snow leopards captured. So I have not separated this by, I have not separated this by number of individuals. This is just the encounter rate on different cameras. C49, it was probably on some snow leopards home range or very close to home range center, or maybe close to 1 or 2 individuals or 3 individuals, which is why it has ended up with a lot of encounters. These ones, let's say C2, C18, C19, they have relatively fewer encounters, and some cameras like C11 has no encounter. It was there in my study, but it has had no snow leopard captures, right? So this is typically how your data is generated. You're dealing with 2 types of data, one trap data, the other is capture data. And to begin with, these are the 2 most important data sets we need. What we do is, don't worry much about the codes right now. What we do is we load this data into the software through via R in R, the package which we call as SECR, which stands for Spatially Explicit Capture Recapture. And using this code, we share this information we share the information about where the traps are and where the captures are to the package. Now, once the data has gone up, there is one more important set of information that we must provide to the software to run the analysis. And this information is called the integration space. Different people In fact, different statisticians give it different names. Some people call it mask, some people call it integration space, some people, I forgot what other, there are many names to it, but there's a general consensus that integration space is perhaps the most most accurate description of what this is called. Now, in other words, when you are providing the data to the software or to the package, you're giving it, all you're giving it is the locations where the camera traps are, and you're giving the number of encounters each camera is getting of different snow leopards. That's all you're providing it with. It needs to use the maximum likelihood theory approach to run through a series of points in this integration space to find out for each point what is the likelihood that this point is the activity center, what is the likelihood that this point is the sigma, what is the likelihood that this point is where I have to estimate if it was the activity center, what would be the encounter rate at this point. So the package has to do it for each point in space. In an ideal world, we would have been able to do it infinite, but it takes a lot of time. So you have to keep this finite. And in other words, this is the space where you will, if it is too wide, then you have challenges. I'm just going to show you if it is too small, then also there is certain challenges. I'll just explain those in the next slide. So, okay, there we go. Yeah. Now, what I'm going to do is I'm just going to zoom into this space, and just to reiterate, the integration space is the space over which the software estimates the maximum likelihood of each of the captured individual generating the detection function of space use around its activity center. Okay, so one reason why in SECR, in spatial capture recapture, we must define the area over which the package is doing this analysis, is doing this integration. Now, I'm just zooming into this, I'm zooming into this little section here, and we'll try to explain why it is important. Now, consider this particular individual X. Now, in this case, this, if I go back one slide, the red rectangle is simply the frame of my camera traps, right? So I've just bound it by the camera trapping frame. And let's say if I treat this as my integration space, what happens in this case is if an animal had an activity center here, it is, if you look at it, there is a certain chance that we might end up capturing it, one of those cameras there. Now, let's take the example of N. Now, N is outside my sampling frame, but it is getting captured in this particular camera. H is just at the edge of it. Maybe it might actually end up being outside the frame, but it is going to get captured, or it has a certain probability of getting captured in these two cameras. Similarly, with the camera Y, with the Snow Leopard Y, this Snow Leopard is moving about in its own range. It has no idea where I have set my cameras, and there will be a certain probability with which Y Snow Leopard will get captured on these cameras. So what ultimately will end up happening is if I keep the study area or my integration space so small, I might actually bias my results very strongly. In other words, I will end up with all these animals counted as them being part of this study area, which in reality is not true. They are outside my sampling frame. So I have a problem here. So what we do is, to make life simple, we try to identify a distance which is far enough from these cameras so that there is no chance that a snow leopard living here, let's say there was a snow leopard X1, there is no way X1 for whatever its activity range would be will ever get captured on any of my cameras. So this integration space boundary is defined to be big enough so that animals from outside do not get inside and get photographed or trapped on our camera. Similarly, what I can always do is, there's no limit to it. I can have an integration space which is this big. How does it matter? It doesn't matter. There are two problems. One, the integrations, the spatial capture, recapture. Just imagine what this software is, poor software is having to do. It is having to run from each pixel to pixel and calculate all those parameters at each pixel. I give it a bigger space, I give it this space, it does that. I give it this much space, it still does that. The bigger the area I get, the longer my analysis will take. And in some cases, you'll be surprised to know that some analysis can take up to 7-8 days, even months or 2 months for just one model to run, because either the space is too big or there are just too many points in that space. So we need to strike a balance that the area is big enough that it ensures animals outside are not getting captured. At the same time, it should be small enough so that A, we are not ending up taking too much time, and B, remember there's another very big assumption that we are making. For whatever captures I'm receiving in this part, I am assuming the snow leopard density is similar in this part. Now that's a big assumption, but we have to make that assumption. Now, maybe there is another covariate which is helping us assess that. That's a different matter. But in this example, we are assuming that the snow leopard distribution is constant or is uniform inside and outside this unit. Now, if I make an integration space which is so big, I am actually going to have to extrapolate and assume and make that big assumption that whatever the snow leopard density was in this little unit is the same here as well. And that can lead to potential biases. It can lead to potential errors, which we don't even know about. One reason why we have to find the smallest, yet the smallest area which is big enough to ensure snow leopards from outside are not getting captured on our camera trapping frame, right? I hope this was clear. If not, we'll come back to it if anybody has a question. So here what I have done is, and the good part here is that spatial capture recapture tools, they do have these functions which can help you estimate we can help you predict the best size or provide the best size of your buffer outside these cameras, which will ensure that you're not biasing your results. Let's say 0.1% or 1 in 1,000 or even less if you want to. Now, okay, so what I've done here is I have created an integration space using the tools available in the capture recapture analysis. And if you look closely, these are little pixels, right? Now there is certain distance between these pixels. What does distance means? I'm just going to explain in a few minutes. But basically, all I've done is transformed the data that we had into this integration space. And if I move to the next slide, yeah, this is where we try to understand the resolution. Now, if you look carefully, each of these points has a certain distance. As I mentioned earlier, we can have infinite number of points here. We can have distance between the points as here. Okay, so look at this point. So the distance between these 2 points can be right now, let's say it's 500 meters. It can be 200 meter. It can be 100 meter. It can be 1 meter. It can be half a meter. If you want to keep it 1 centimeter, just put it 0.001, whatever. It doesn't matter. The analysis will still work. The analysis will still work. The problem is, for the more the number of points you're looking at, the more intense and the more time consuming your analysis will be. So you have to find strike a good balance here. Now look at these images on the right. Now this is a case where I have created this detection function, this half normal function with a spacing of 50 meters. This is the case where I think we created it for, I think 200 meters or something like that. Let's say 250 meters. And in this case, it was it? Yeah. In this case, it was, sorry, this second one is 100. And the third one is, say, 250. Now, not our example, but a hypothetical example with different variances. Here, the sigma is 300. Now, for a small sigma, if I am taking the distance at 250, automatically what I'm ending up getting is just these 2 points. That's all. That's all I have to estimate my my detection function. In this case, I do have more than 2 points, so I do have at least some area to play with. The more you have, the better resolution of your detection function. The only cost here is the time, right? So the resolution at which the histogram is created. So if it is too widely spaced, you might end up with too few bins to even detect the variation. If you have too many bins, then it's just going to take too much time. So we typically choose space between pixels in a mask to be small enough so that we get at least 5 to 6 or maybe about 10 bins. In case of snow leopards, the resolution of the pixel points on this integration space is typically about 500 meters, which allows us to get anywhere between 7 to 10 bins. So for a snow leopard activity range, it would be this big. So we will have enough bins within these to create a detection function, assuming the female home range of around 90-95 square kilometer. So given that roughly we keep it around 500, but that's not standard. You can decide for your own study area, and this process takes a bit of back and forth and a bit of an iteration where you try a few things and then you come up with the most optimal number. What you can also think of here is you can assume that at what distance will the snow leopard density actually start changing as well. So because what the estimator does is it estimates density at each of these pixels. Snow leopard density at each of these pixels is estimated, and then we get the total of the whole study area. So you can even use that parameter as one of the defining factors. But in other words, the best way to take it is you know roughly what the activity range would be. You know what the sigma would be. Keep the pixels small enough so that you have 8 to 10 bins within each snow leopard's activity range, and at the same time don't make it too small so that you end up with too much of data to deal with. And that's so far has seemingly worked okay. So there's no fixed guidance on this. You have to take it a bit intuitively at that point. So anyway, so this is what our space looks like. Now I'll just show you a quick data summary. When we ran this capture recapture analysis, this one, where we captured snow leopards which were within a certain which were trapped on these camera traps. When we ran that analysis, we end up with the data that looks like this. So we have in total 17 animals detected. We had snow leopards detected 387 times on different cameras. Now that's a very big number. We usually don't end up with that much, but let's say here I had set up, it was a high density area, whatever. Out of 50, 41 camera traps had detections. And of course this is 50, but out of 50, we had snow leopards detected on 41 cameras. Now, some of you might remember we had 26 snow leopards in our study area. This one is saying there are only 17. What's happening here? what's actually happening here is, look here. We have Snow Leopard A, which has gotten almost 60 encounters. Snow Leopard B has got just 1 or 2 encounters. Snow Leopard C has another 50 encounters, and so on. T, maybe some camera was right at the activity center of Snow Leopard T, so it has a lot of encounters, almost 70, 80. But what about Cat F, G, L, M, O, P, R, V, X? What happened to them? They were in the study area. They were part of our study. What happened? And this is a question that a lot of people will ask you if you're setting out camera traps to do population assessment. People often ask that there is a chance that not all snow leopards will get captured. And a very common question, at least on social media here in Kyrgyzstan, is that you will never get all the snow leopards on camera. So how good are your results? The bottom line is that's the starting point. We are taking this assumption that snow leopards, we will never, at least in the wild, there'll never be a situation where we'll be able to capture each individual. You might recollect this devil we discussed last time, earlier in this session as well. Now, all that's happening is that this devil is in action. So the number 17 is the number of animals, which is this. If I divide it by some probability here, which is of course this little red devil, I will be able to come up with the right amount of density. And how do I do that? I estimate that probability as a function of this detection. So if I had animals with activity centers, or if I had camera traps which were away from animal activity centers, I am certainly less and less likely to capture them. So there is a possibility that these snow leopards, F, G, L, and M, they didn't have a camera very close to their activity center. It is quite possible. And that's exactly what must have happened, which is why we've not got them on camera traps. And that's a fair bit of assumption. Ultimately, when I run the analysis, don't worry too much about these codes. We'll hand over all of these to you to do your own analysis. But when I actually ran the analysis on this artificial gummy bears or artificial snow leopards data, this is what my estimates are. Now, these are models because ultimately what we are doing is we are modeling the density and encounter rate at activity center and the ranging pattern as a function of its distance from the activity center. So all of these are getting modeled as per this function. The estimates are here, but the most important estimate for me, at least at the time being, is abundance. You remember we had A to Z, 26 snow leopards. Out of them, what we have captured here is, what we have estimated through our spatial capture recapture is 25.4. With an error of 21 and 36, I think we are fairly close to reality. And with that, we will stop here. I think I've already gone over time by 12 minutes. But if you guys have some time, please feel free, because we need your inputs in the next slide, which is sort of a quick recap on what the SCR assumptions are. And in the meanwhile, while you help put these assumptions up there, I will try to go through some of these questions.
Yeah, so I listed some of the kind of assumptions to give you guys a head start, but it's not all of them. So feel free to list other assumptions for SCR models in the chat.
Okay, can you please start writing, or at least switch on the mics and let us know what are the key SCR assumptions?
And just, I mean, you guys, we know it's a steep learning curve, but today was really just to get you guys thinking about SCR and how that relate, and understanding really the parameters and the assumptions behind it, because those are really important for then thinking, how do I plan my survey? So that's why we really want you to go through these. We got one, Koustubh.
Yeah.
Oh, but it's a question.
Okay. Yeah. So.
Oh, but Helena has given
yeah.
a.
Sure. So you want me to let me write down these, but I think we have a very good question from Barkat, and I think we should be able to address that right away. Then we have Justine, then there was a question by Helena. That's okay. Oh, well, I'm completely lost. Justine, can you help me with the other questions?
Sure, sure. We also have some of the assumptions coming. Koustubh, should we do that first? And then
Yeah,
we
let's
can
do
go.
that first, and then we can go to the questions.
Yeah. So I have one from Helena saying closure assumption, like demographic closure is one assumption. And I think this relates to the beginning of your presentation, Koustubh, when you were sharing how the activity range changes, right, for different seasons.
Yeah.
So it's important. And I think this is also with our coloring data, right? If you take a whole year's coloring data, the range looks massive. But if you only take a month or 2 months, it's much more concise in a certain area.
Yeah, perfect. Okay, population closure correctly, yeah.
And now snow leopards correctly identified.
Yes. Good. Barkat, don't worry, I'm going to come to your question. I'll come back to it.
Never perfect detection is another one from Bakat. He's saying the detection probability is never 100%. And we have another one, which I think is from Elena, that detection changes related to activity centers.
Sure, that's the same thing, I think.
Yeah, related to the same thing. And one from Iftikhar, who's saying the integration space, which is the mask.
Iftikhar, can you please elaborate? I've written half a sentence. Can you please elaborate? What should I write beyond this? Should be? Okay, I'll finish this.
So I shared in the chat the publication related to this that recently came out and highlights how in small study areas, if you have like really small, only a few camera traps, maybe in only 100 kilometers squared, for example, and assume that you are capturing the entire kind of population of the snow leopard, then you might positively bias you do positively bias your estimate. There's another one I see, which is independence assumption, Koustubh, that different snow leopard individuals are independent of each other. For example, you would not take a for example, a mom and a cub traveling together as two separate individuals.
Okay, Barkat is saying integration space should contain all possible activity centers from where animals can be detected. Fair enough. I think that's this point here. Barkat, does this point address what you are saying? Yeah, Iftikhar. Very good. Fantastic. Yeah, between Barkat and Iftikhar, I think we have the right answer. Okay. Anything else, Justine? Mating pair capture. That's a very good question. Okay, we'll just answer that now. So yeah, so Ranjana, I mean, if a mating pair is together and throughout your sampling they're always getting captured together, then you do have a problem that two animals are going to have exactly the same detection function and will kind of accentuate the shape of the curve. So you might want to, if your sampling is really short enough and you have all the encounters where both of them are always together, just ignore one of them. That's a problem. That's a problem animal. But typically what does happen is they come together and then they go away. That's all right. As long as their encounters are sort of random in space, it doesn't matter. And then of course they come together, spend a couple of days to a week or so. But it doesn't happen so that male, female are walking together for 3 months or something. That doesn't typically happen, at least none that we know of. So that in that case, it should be fine. It should be big enough to cover. Yes, thank you, Iftikhar. Now there are a couple of very good questions. So can we take a couple of questions, Justine? Do we have time?
Yeah, sure. So I think just thanks if you guys want to stay for another 10 minutes for questions. But the assumptions there, I think that covers everything, Koustubh.
Yeah.
The ones you listed, the main ones.
Okay.
So we can go to questions. Do you want me to help you with that, Koustubh? Because there's a lot of text. So I think, and for those that cannot stay, feel free to leave. We won't be offended if you cannot stay for the questions because we are over time. You obviously were really into SCR. So we're staying, but if you can stay, please do, and we can answer people's questions.
Now, Barkat has a very interesting and a very valid point that what if this is the activity range? We are assuming that space use is linear, right? Okay. Now, this might be the case when you have some animals moving in the savannas. In reality, and I have to tell you this as well, that suppose these are the contours of a mountain, right? Now, if there is a snow leopard living here, and we're talking about pretty high mountains, okay? So this is a very high ridge line. Now, if there is a snow leopard living here, for this snow leopard to go this side, it would rather go like this, not like this, right? And this is the kind of barrier that you're talking about, right? Now, what happens in this case is you're talking about not linear distance, but ecological distance. Or in other words, if I am a snow leopard, I have to go from point A to point B. I'm not going to take the straight line path, which if it was a plain area, I would have done. But in this case, I would take the path which will cost me the least. Now, what I can do is to model this, there is a way, and there are two very good papers, one by Andy Royal and his colleagues, the other one by Chris Sutherland and his colleagues, which use ecological distance to estimate the same detection function as a function of this was distance straight line. All it does is it now estimates distance as a function of the least cost path. So from here to here, if the cost, let's say we add some cost to climb up and climb down, let's say the cost was 10, and to walk this extra distance, the cost was 7, it would treat this. So the range would end up becoming like this. So the snow leopard might end up with a home range like this. And each of these sides, now this is high cost, this is high cost, this is low cost, right? So it's easy for an animal to go from here to here, but it is difficult for an animal to climb up. It's again easy to go from here to here, but difficult for an animal to climb up, and so on. Now, this kind of an uneven space use does happen, especially with snow leopards. In fact, we're just finalizing one manuscript which should be out soon, where we explored this in one of the snow leopard habitats, and we did find a pretty strong evidence of snow leopards not preferring low areas, but they prefer the ridge lines, which is also true, right? Snow leopards love to walk on the ridge lines. And in this area, they would prefer being on the ridge lines, like rather than going down and changing altitudes. You know, it's much more expensive for them to go down and come back up and go down. Instead, they would just prefer to be on the ridge, you know, skywalker, as you might want to call them. So yes, so those models, these variations can be modeled. You can model the distance as a function. Sorry, let me clear this. Yeah, you can model your sigma as a function of you can call it function of least cost distance. And that's a fair bit of assumption. You can do that. So these things can be done, and there are models which can take care of these. The only thing you need to remember is that sometimes, you know, your barriers, I mean, from here to here, there is a bit of a barrier here, and the only way to go around it is like this. In a large number of individuals for a large number of data, it kind of averages out, right? If each snow leopard is having the same, is having a similar mosaic of undulating or obstacles to cross over, then it somewhere averages out at some value. And spatial capture recapture methods are incredibly robust to these variations. All you will end up with is, instead of this one line, you will have an error, which is somewhere like this. Doesn't matter, as long as it's robust enough and it's not, it's a reasonable estimate, it will still give us give us the density. So there are times when it becomes important and you can test it, you can investigate the effect of it, and many times you might end up finding, well, it doesn't matter. So you can use the information theoretic approach to investigate whether this is happening or not. Oh, sorry, Barkat, you got dropped. We'll send you a recording.
There was another question, Koustubh, about why it takes so much time. I mean, you were saying about computing such large areas, or with small granular kind of you know, versions of the mask. What Helena was asking, why that would take so long. I mean, what was being used to do that analysis?
So Helena, if you know maximum likelihood, for every estimate, now let's say the maximum likelihood of me getting 5 heads in a toss of coin, if I have to find the maximum likelihood of this, what I will do is I will create a space and I'll test P is equal to 0.01. Let's say, I mean, if I'm taking just 2 decimals, so I will estimate the binomial likelihood of me getting 5 heads for a P 0.01, and I will get some certain value of that likelihood. Then I will test P is equal to 0.02, 0.03, 0.04, and so on, all the way till P is equal to 1. So I'm really going through 100, in fact, 100 iterations here, right? Now, this is a simple binomial likelihood of getting 5 heads. And there will be, at some point around, if this is 0.5, I will end up with a bit of a peak. And it'll say, okay, so the probability of getting 5 heads is 0.5, right? Now, if I have to say what is the probability of me getting 3 heads, and then you do the same thing and you will end up with a certain probability and it'll peak up here. You can use the binomial likelihood function here. So what you're seeing here is, for a single variable, the maximum likelihood solver is going through to all possible values. What happens in case of maximum likelihood based estimation of spatial capture recapture for, in this case, for 3 unknowns, it does that for each pixel. So for each pixel, it goes through an entire range of clear it like this. So for each pixel, it does a likelihood estimation of all the three variables, all the three parameters. It estimates the most likely value of sigma, it estimates the most likely value of lambda 0, and estimates the most likely value of density. And it does it for each pixel. So if I have 5 million pixels, you can imagine the amount of time, because for sigma from the minimum possible sigma to the maximum possible sigma, lambda 0 from minimum to maximum, density from minimum to maximum. Even though the solvers are very optimized and they take the last value to do this, to do it for that many number of times will take that much longer. And that's why we try to kind of keep a bit of a balance. But if someone has the time, there's nothing stopping you. You won't do anything wrong. It's just going to take a long time. And the value, whether that analysis will be, that time will be worth it. So you have to do a bit of a cost benefit analysis of time as well, how valuable it'll be. Okay, I've heard it. Least cost ecological path, makes sense, got it. Sub question, how cost is defined here? You define cost by whatever you think is affecting. In Mongolia, snow leopards are affected by whether it's a plain area or a rugged area. They don't like walking so okay. So if this is, oh, actually we can show you on the PowerPoint that we had. No, that'll be easier. Just give me a minute.
Koustubh, and if we take one last question, we'll answer
Sure.
by email, because just
yes, of course. Yeah.
Everyone.
So just to show you, like here, over here, now these are rugged areas, Barkat. These are flat areas, okay? Now a snow leopard, if it is somewhere here and it has to go here, it would rather go like this than like this. Now here what we are defining cost, we are testing the effect of ruggedness as cost. In another example, let's say I take the example of Spiti, for instance. Now a snow leopard might have to go from here to here. It's all rugged, so ruggedness really is not changing. Maybe now I might want to test whether there is an effect of altitude. So you decide as an ecologist what you think could be affecting a snow leopard. Now, if you have a river and you are 100% sure that the snow leopards don't cross it, or you think river adds as a barrier, use the river as a barrier. Use it, give it a value which is, let's say there is a value 0 and a value 1 for the river, and then the cost of crossing river, it's almost like, from point A to point B, the cost goes like this. So it will avoid crossing on this side, but would rather go much further on other side. So river becomes a resistance in that case. You can define the mass. Okay. Helena, size of the data for 7 days of a run. Which 7 days, Helena? I didn't get it.
I think because you gave an example that one case it could run for 7 days, but that depends on on the data set. She's asking what data set took 7 days to run.
Oh yes. So to be some of these, the same analysis which I showed today, which was the estimate which I showed, it took using maximum likelihood, it took about half a minute or so. If the same analysis I was using Bayesian methods, it would have taken at least a couple of hours. If I was using SPIMS, the same analysis would have taken maybe half a day or one full day. So sometimes the same analysis can take different time depending on what method you're using. And the longest, I think, some data set that I've worked on was one from Pakistan, actually, with Ali and his team. And yeah, each model, they used to take almost 1.5 days, just because the size of it. It was huge area, several thousand square kilometers. The other one was from Nepal, where I worked with Madhu Chetri, and that data set again almost of, I think, 20,000 square kilometers, much longer than we would have anticipated it took. So yeah, again, 3-4 days, 6 days per model. So okay. Any other questions?
So maybe we'll end now, if possible, and then encourage people to send questions. But we might start the next session, right, with a question answer, because we would like everyone to maybe go home, see what, if they think, because it's a lot to take in one go, maybe rewatch the recordings or read more the PAWS manual to get more an idea about spatial capture, if this is especially your first time being introduced to it. But next time we're going to do question and answer, so please prepare some questions for us. And then we're planning to work on that big bottleneck Koustubh mentioned, which is related to individual ID. Because any model you have, if you put the wrong data in it, of course it's going to give the wrong output, right? So we need to prepare our data to make sure it's as correct as possible and is representing our population as possible. So we're going to talk about that next time and ways that you can help promote this in order to have really good identifications of your different individuals. Yeah, so I don't know, any of the last things you want to say, Koustubh, before we leave everyone?
Thank you for tolerating me for an hour and 15 minutes non-stop. I'm really sorry for going so long, but yeah, yeah. But thank you, and again, really grateful for all the questions. If there are any we have missed, I'm sure we can follow up on email. Raki and Justine have set this wonderful Google group where be assured there'll be some questions we won't know the answers to, and we can always escalate them to the right people who know things much better than we do.
No, Koustubh, it was a great session. Thank you so much for using all of these animations to share with us, because the spatial recapture is not a simple model, and it's hard to dissect it. And I think you really articulate it really well. So thank you, Koustubh. We're really grateful that you took the time to share with us. And also bring it so into snow leopard ecology, which I think is the hardest part. You have a model and then you have snow leopards, so it's bringing it together, right? That's the hard part. But if anyone has questions, please email us. Also, just a heads up before you leave, the PRAY module applications are due today. If you're interested in applying for that, please go for it, or write to Raki, ask any questions, and apply today. Otherwise, we will be sending an email with a few things maybe to prepare for next week. But yeah, thanks, Koustubh, and thank you everyone for the great questions.
Thank you, Justine. And Raki, thank you so much for
managing
the whole room.
Thank you so much.
Thank you to Raki for being our rock for all these sessions. Raki,
and thank you to you all. Thanks to you all, seriously.
Yeah. And Ranjini for joining us.
Oh yeah, Ranjini.
Yeah, thanks, Ranj.
Oh, there she is.
Thank you,
Ranjini. Thanks for a great session, guys. It was really wonderful. Thank you, Koustubh. It was amazing.
Great. So then everyone can leave. I might stay on the call with Koustubh. Raki, do you want to stay on?
Yeah.
We'll say goodbye to everyone else. Thank you all.
Have fun. See you later.
Have fun.
See you next week.